Greetings, everyone. Thank you for taking time out to join in on this segment of the Life Scientific Lunch and Learn series. For those that don't know, my name is Mike Bellum. I'm the founder of Life Scientific, a company we launched in 1992 to represent manufacturers of parenteral and related production machinery. We facilitate these lunch and learn sessions at least once a month, typically at 11:45 on the third Wednesday of the month. Every once in a while, we'll have additional content that we'll post and send out. If you want to stay current on the educational material that we're going to be providing, just join our LinkedIn, the company LinkedIn page, or our YouTube channel to make sure that you're kept current on the topics that we're going to be discussing. Some of those clearly are going to be relevant to your work, especially something like today's, if you're doing any projects involving tanks and heat transfer systems. So glad to be able to get some of this type of content to you. Just a little heads up on navigation. This webinar is saving to our YouTube channel as we speak. There is a little bit of a delay on it. You can certainly share the live stream with anyone that may benefit. All you have to do is just send them the link from our YouTube channel or the LinkedIn company page, or we have links for this and the 3 previous lunch and learns that we started doing earlier in the year on our website, lsi1.com. So, okay, just about the navigation here on the screen, you have 2 options. You can view in full screen, which may be helpful when some of the calculations that Kyle's going to be going through are up. You may want to click on this box to send it into full screen mode. But during the presentation, if you have any questions, what you would want to do is hit escape to minimize from the full screen view, and then your chat box will come up. And any questions, which all topics relative to heat transfer and tanks are fair game. So even if it's not directly related to the content that Kyle's providing, I'd suggest popping a question up if you got any tank situations that you're dealing with, and just type them here and then hit the send button, and those will be collected. And towards the end of the presentation, Kyle is going to address the majority of those questions that come up. So again, you have the option of going full screen or just hitting escape and typing there. Unfortunately, if you're currently not seeing the feed or have a black screen, some older operating systems aren't compatible with this live streaming function. But fear not, you can come back to the content after it's over. So in about an hour, hour and 15 minutes, it'll be up and you will be able to watch the stream from the YouTube link. The only disadvantage is that if you have any questions, we won't be able to address them live. However, if you email any of us from Life Scientific those questions, we will make certain that they're addressed for you. So as mentioned before, Life Scientific specializes in the representation of production equipment for parenteral and general pharmaceutical, food, beverage, and the chemical industries. We're based in St. Louis with project engineers that help us cover a good portion of the Midwest. So we handle lines from the aseptic environments through typical production related machinery, some testing equipment, and all the way down into the packaging area. We've had the pleasure of working with JV Northwest, known as JVNW or JV, for quite a few years. First, they were a supplier to one of the equipment manufacturers we had handled. And for the past several years, we've represented them throughout the Midwest. JVNW has been at the tank business since its formation in 1981. They're ASME code tank fabricator, adhering to 3A sanitary and CGMP standards. They have a very broad range of highly customized tanks that are going to a variety of different industries. They will manufacture tanks up to and beyond 50,000 gallons. And over the years, their shop has grown to more than 50,000 square feet. And they do a very good job of keeping it full all the time. They have a comprehensive range of in-house engineering to facilitate product and assist with process design. JV has a full service in-house rheology laboratory. How many know what rheology means? But anyway, the lab is to assist with complex mixing. So JV's got a full range of mixers and can bring product into the lab and help establish what might be the best way and type to mix your product in their lab. So please get with us if you do have any jobs that maybe we can quote, or if you'd like to schedule a time to go out to their facility and audit. We certainly welcome that opportunity. Today, our presenter is Kyle Sawyer, a gentleman I've known for far too long, and obviously he's a much better football player than I ever was. I just made it through high school, but while he wasn't on the field at Missouri State, he managed to get his industrial engineering degree. Kyle got his MBA from Drury, and he's pretty much been in the tank business since graduation from college. He's been with JV since 1997, and while he's been involved in spearheading several plant expansions and also a couple of different very appropriate patents. Today, Kyle is a partner and COO for the company. He's going to give us a 400 level class on heat transfer and BTU load determination for tanks and vessels. So please do remember that if you have any tank related questions, go ahead, put them on the chat. Kyle is a wealth on any related topic. So with that, I'll turn it over to Mr. Sawyer.
Thank you, Mike, for that kind introduction. I appreciate that.
My pleasure.
I'm going to jump right into the presentation. I want to make sure my screen does show up. Thank you. So today I'll be talking about heat transfer and actually how to determine the surface area required for a tank or a vessel. In the first slide, you can see the jacketed area is that dimpled pattern. Now, I prefer dimple pattern for efficiency of heat transfer. And what it does is causes a nice turbulent effect, and it's very efficient for moving the cooling or the heating fluid or media into the tank. To determine how much heat transfer we need for a vessel, we first have to figure out the BTU loads for a vessel. So it's a pretty straightforward calculation. If you'd like to pencil along with me, you're welcome to. I will give a live example, and you will be able to see how the numbers crunch together. But first, you need to know the gallons in the tank, the pounds per gallon of the solution. So let's say if it's water, you can use 8.34. The specific heat, and then the temperature change. And when I say temperature change, that is the starting temperature of the solution in the tank, and then the ending temperature in the tank. And so there's a difference, or we call that delta T. And you divide all that by the time that you want the heat transfer to occur, and that will give you your BTU loads per hour. So let's give you an example. So you have water in a tank. It's 1,000 gallons. We're going to agitate that water or mix it. We're going to use steam as our media. We have 1 inch of insulation fully around the tank. We want all of our heat transfer to happen in 1 hour. Our starting temperature is 60 degrees. Our ending is 170. The ambient air outside of the insulated tank is 55 degrees. The tank is 5'6" diameter. The wall height is 5'9", and it has an ASME dished heads on both ends. So it's really just a plug and play with the formula. We simply put our gallons in at 1,000. Our weight of water is 8.34. Our specific heat is 1. Our change in temperature inside of the tank is 170 minus 60. Divide that over an hour, and you get 917,400 BTUs per hour required inside of for the energy used. Now, we also have to figure out how much heat we're losing in the vessel. So I think I'm going to give you a handy little chart that you may want to reference later or copy. But in this chart, we can look at insulated or non-insulated tanks and how much heat load we're going to lose per hour per foot squared. So if we back up just one step in our example, we did look at the tank diameter in the tank wall. And I may go through this a little bit quickly for some of you, but I'm going to give you the square footage of the vessel on the outside. And the square footage is going to be 150 square feet as this pops up. So the area of the vessel, 150 square feet, multiplied by the surface load found on the chart I gave you. And on the chart, when you have a chance to go back and look at it, you can find 1 inch of insulation fully around the vessel, and you can look at the surface load loss, which on the chart, I picked one purposefully that is between two numbers to show you can interpolate between numbers on the chart and use that number. So it fell right between 44 and 48 heat load loss, so I used 46. So that just adds an additional 6,900 BTU per hour required. So then we just add those two numbers together, the 917,400 plus the 6,900 BTUs per hour, and get our total load required. Now let's look at the log mean temperature difference. And in determining the log mean, I like to produce a chart, a little T-chart. And so I have one here in front of you, and I write the words out every time, handwrite it, start, end, product, media, and then I take the differences. So in our example, we know our starting and our ending temperatures. Oops, I'm sorry, I went the wrong direction there. We know our starting and ending product temperatures. For steam, our starting and ending, we can assume, and this number does work, no temperature loss. But if you want to plug in a couple of degrees, or if you have actual data showing you are losing, you can go ahead and show a loss. But our product starting at 60 and our media starting at 298, we just take the difference, 238. Our product ending at 170, our media ending at 298, we just take the difference of 128. And then we can plug right into our formula of the log mean temperature difference. So 238 minus 128 divided by natural log, and you'll find we get 177 degrees F. Our next important value on determining the surface area is a U value. And you're able to reference this chart later as well, and I use this very chart every day. It's been years of data gathering and actual and lab data gathering. So this will be very helpful for you when figuring out U values through the walls of the vessel. So in our example, we need to choose our U value, which we chose 125. And if you'd like me to back up for a second, I'll show you why I chose 125. But we have steam, water. So if you look at the chart, steam, we're doing water at the first line. And it gives us a range from with no agitation of 100 to 225, with agitation of 120 to 300. In our example, we were in an agitated tank. So I did use the agitation column. I'm a little more conservative and when I do calculations, so I chose closer to the 120 than choosing to the 300. So I'll move forward with our example. So we take our total load, which we summed up earlier, multiply by our U value and also our LMTD, and that gives us the actual surface area required on the vessel to perform the duty we required for our heat up from 60 to 170. It calculates 42 square feet. As a general rule of thumb, I multiply by 1.25. It's just a fudge factor. Sometimes manufacturers may not have as efficient of a jacket as we believe they to have, so we need to just take a close look at that or use the 1.25. Now, you may not have enough area on the vessel to fit the jacket, so then you may have to use a factor of 1.1 or just 1.0. So your calculations become very, very critical at that time. A nice note, in doing steam, we did not do a GPM step, but if you are using glycol for cooling, gallons per minute does become important. And you should always consult your manufacturer of what their minimum gallons per minute is required through their jackets and what pressure drop. That's important because the speed of the fluid going through the jackets does have an effect on how well the heat transfer is working. So you're more than welcome to come back and reference this calculation to walk through this calculation. The final note, transfer of coefficient, that's the U value, times your jacket area, times the difference of your product minus media, gives you an initial demand on BTUs. And so what I like to do is when I do the calculations, I put a nice little package together of initial demand, full load demand, and average demand on BTU jackets to give that to our, for example, our boiler guy who's going to supply a boiler. Then he knows what that particular tank is going to demand. Or if you have 3 of them, then he knows, wow, I've got to supply 3 tanks with this many BTUs. You can do the same. That same information package can go to your cooling or your glycol supply company, and they can help you determine the size of the chiller that is needed to cool the tanks down. So now I'll leave this open for questions. I know I went through this quite quickly. If you have a tank specific question that's kind of complex, and if we can't answer it over this seminar, I would be happy to take an email and I can help you solve your problems. And Mike, shall I turn this back over to you? Okay, there's a question that asks if we can explain the different types of heat transfer jackets. and related efficiencies. There are basically three main types that you will see in the industry, and that is an open jacket or an open flow. So that's just a free-for-all happening between the walls of the tanks. Typically, there's no baffles. There may be a few. You'll have less turbulent flow. It's a little bit less efficient. And the pressures that you're able to achieve from your glycol system are much lower. You'll have dimple jacket. Now, dimple jacket, you have a little bit of a trade-off with pressure drop because there's a high drop through the jacket. So then you have to size your pump that pushes the media through the tank wall, but you do get a very efficient turbulent flow. So your U values then can be a little bit higher. Now I know in the example I gave a very conservative U value, but you can use a little bit more aggressive U value when you're using the dimple jacket for the turbulent flow. And then the final kind of jacket that you'll typically see will be half pipe coil or spiral jackets, they're called sometimes. Now with half pipe, you can achieve very, very high pressure. It has low pressure drop through it as compared to dimple. And it's very good for viscous or high thick solution or media or oil media going through the jacket wall. Another question came up and it popped by me a little bit fast, but it was, are there different types of insulations? And there are. Our company specializes in stainless steel tanks, so we use chloride-free insulations. I think that's very important. If you're doing steam heating, we paint with a Thermalock barrier paint, so then if there happens to be any chloride corrosion coming from the outside of the vessel or any spray down or solution in the CIP that may be migrating into that insulation, it keeps a barrier between the jacket wall and the insulation. These are applicable to spirit distillation processes, and typically like in mash cooling, when you're cooling your mash or your ferments, it's very applicable. Now, there are similar calculations for when you're going ahead and doing the distillation process itself. Media flow is very important when you're using cooling jackets. One, you do not want to go under the minimum of the manufacturer's recommended flow because of the turbulence that's required to transfer the heat between the media and the tank wall. So the higher the flow, basically you get a better U value. So a little bit higher U value is what you can use when you're doing these calculations. So flow does matter. Now you do not want to go higher than the manufacturer's recommendation either. So for example, mechanical dimple jacket, you'll have a nice flow in the range of 20 to 30 gallons per minute per jacket zone. And that's a kind of a sweet spot. When it's resistance welded dimple, which you see on a lot of wine tanks, you have a flow of around 10 to 12 GPM. And that's the sweet spot for that type of jacket. So if you have a specific jacket and you want to email me the question, I'll answer that for you. So the typical pressure in a jacket loop, each jacket zone of resistance welded jacket may have an average. This does matter by square foot and surface area, but it'll have on the average approximately a 20 to 25 psi G pressure drop across each zone. So it does matter. You have to size your pump to overcome that so the fluid can go through at the correct GPM with the correct pressure drop coming on the outlet side so you can get it back to your system and recirculate the loop. And it looks like that's all the questions.
Okay, well, hey, Kyle, thank you so much. We really appreciate your taking time out to help impart some of your wisdom upon us. Our next lunch and learn segment is going to be presented by Steve Ferguson from Bonson Environmental Specialties. It'll be on October 18th at 11:45. Steve's going to be comparing and contrasting a typical freezer farm configuration versus a consolidated approach for ultra cold vaccine storage. So if you do have any significant vaccine storage at your facility, this absolutely is going to be appropriate and meaningful content for you. So again, my thanks to Kyle and everyone involved in getting this set up, and to everyone attending. If you need additional information, have any questions, you can send an email to the link on our website or give us a call. We'll be glad to help out as possible. So also remember, you can share the webcast link from our YouTube channel with anyone that may benefit from the content. Those that are trying to plan these out for your facility, certainly this BTU information is relevant. And if you need some one-on-one time with Kyle to get things set up, we're more than happy to facilitate that. So again, thank you very much. If you've got any tank projects we can quote, we'd certainly field those as well. Hope everybody has a great rest of the week. Thanks, Kyle. Talk to you all soon.
Thank you, Mike.